All right, so you want to know how AI can, like, create something out of nothing?
Yeah, it's pretty wild stuff, isn't it?
Well, you sent over a couple of academic papers about this score-based generative modeling thing, right? With these, what do they call?
Stochastic differential equations, SDEs for short.
Right. SDEs, that's the stuff we're diving into today. This stuff is really on the cutting edge.
Definitely. And the applications are mind-boggling. We
Yeah.
could be talking about, generating realistic images or music.
Or even modeling things like protein structures, which you specifically mentioned. But first, we need to understand how these models actually work. The first paper is called Score-Based Generative Modeling Through Stochastic Differential Equations. It's like the foundation for everything we're going to talk about.
Yeah, it really lays the groundwork. So imagine you take a picture. Let's see a picture of a cat.
Okay, got it.
Now imagine slowly turning that picture into just pure noise,
Yeah.
like completely random visual noise.
Like just a jumbled mess of pixels.
Exactly. That's the first step. Now, the amazing thing is that these models can learn how to reverse that process.
So they start with the noise and then what? Rebuild the cat picture.
Yeah. Step by step, they transform that noise back into the original image
How do they even know how to do that?
by learning something called the score of the data distribution. It's kind of like a guide that tells the model how to move through the noise to get back to the original image.
That's pretty cool. And the paper talks about these two existing approaches that kind of already do this. Score matching with Langevin dynamics, SMLD, and denoising diffusion probabilistic modeling, DDPM. Can you break those down for us?
Sure, both SMLD and DDPM, they both work by gradually adding noise to the data, just like we talked about with the cat picture.
Right, turning the cat into noise.
But the difference lies in how they reverse the process.
Yeah.
Imagine SMLD as taking tiny controlled steps back through that noise, guided by the score.
Okay, I'm kind of seeing it.
DDPM, on the other hand, is more like taking a series of probabilistic jumps back to the original data. It uses a whole bunch of models to do this.
So they both add noise, but reverse it in different ways. All right, I think I'm following so far. Now, where do these SDEs, those stochastic differential equations, come into play?
Well, think about it this way. SDEs are really a way to describe how something changes over time because of random influences.
Okay, so in our case, it's the data changing as we add noise. Right?
Exactly. And what this paper does is generalize that noise addition process. Instead of those discrete steps we talked about, SDEs let us think of it as a smooth, continuous transformation.
So instead of suddenly adding a ton of noise to the picture, it's more like slowly fading it into the noise.
Precisely. And this continuous view gives us much more flexibility and control. The paper proposes using a forward SDE to transform the data into noise, and then a corresponding reverse time SDE to transform that noise back into data.
And that's where that figure 1 in the paper comes in, right? It shows this whole data to noise to data transformation visually.
Yeah, it's a great visual, like watching the picture fade in and out of existence. And the really key idea here is that the reverse SDE only needs the score of the data at each point in the noise. And thankfully, we can estimate that score using neural networks.
So we're teaching AI to see patterns in the noise that lead back to the original data. That's wild. And you mentioned that this whole SDE framework comes with a lot of benefits, like flexible sampling, controllable generation, and a unified framework.
Yeah, those are some of the big ones. Flexible sampling basically means we have more choices for how we generate new data from these models.
Mm-hmm.
Controllable generation means we can, to an extent, guide the model to make specific kinds of outputs. And the unified framework, well, that's exciting because it pulls existing methods like the SMLD and DDPM we talked about under one umbrella. It gives us a deeper understanding of how they work.
That makes a lot of sense. Now, the paper also dives into some specific types of SDs, like variance exploding, VE, and variance preserving, VP. What makes them different?
Remember how we talked about SDEs describing how the data changes with noise? Well, these different types have different characteristics in terms of how that noise affects the data over time.
So it's not just about adding noise randomly, it's about understanding how that noise behaves.
Right. Think of it this way. Imagine adding drops of ink to a glass of water.
Okay, I'm with you.
With some inks, the color might spread out really fast and become super intense. That's kind of like a variance exploding SDE. The noise spreads quickly and has a big impact on the data.
Gotcha.
But with other inks, the color spreads more slowly and stays more contained. That's more like a variance-preserving SDE. The noise is more controlled.
I like that analogy. So VE is like wild, fast-spreading ink, and VP is like slow, controlled ink.
Exactly. And the paper even introduces a brand new type of SDE called a subvariance preserving SDE. This one's great at preserving the original data, which is really important for tasks where accuracy is super important.
So even more controlled than VP. Interesting.
What's really cool is that the paper shows how those SMLD and DDPM methods we talked about earlier are actually specific examples of these VE and VP SDEs.
So we found this hidden connection between these seemingly different approaches.
Precisely. It gives us a new way to understand SMLD and DDPM and opens up possibilities for new sampling procedures and models. And speaking of sampling, that's how we actually generate new data from these models.
Okay, so we've trained our model. It understands how to navigate through the noise. How do we actually use it to make something new? It sounds like there are a bunch of different approaches to doing that.
Yeah, there are. And the paper breaks down a few of them. There are general-purpose numerical SDE solvers, reverse diffusion samplers, and then something called predictor-corrector samplers.
So it's like we have this toolbox with different instruments for creating things from our model.
Yeah, I like that. The general-purpose SDE solvers, those are like your basic tools.
Yeah.
They work, but might not always be the most precise. Then you have the reverse diffusion samplers, which are more specialized. They're designed to, simulate the reverse of that noise addition process.
Okay, makes sense. And then we have these predictor-corrector samplers. Do they kind of combine the best of both worlds?
Exactly. They use a two-step process. First, they predict where to move in that noise space, and then they correct that prediction based on the score of the data.
Ah, so it's like a more refined approach.
Yeah, it leads to more accurate and efficient sampling, and if you look at Figure 9 in the paper, you can actually see how much better these PC samplers perform compared to just using the predictor.
Oh yeah, that visual really makes it clear. Those PC samplers are doing something special. The paper also talks about probability flow ODEs, which seem even more complex. What are those all about?
Well, probability flow ODEs are really interesting because they offer a completely deterministic way to generate the data. It's like having a precise blueprint guiding the creation process.
So it's totally predictable, unlike the other methods that have that randomness element.
Exactly. And that predictability has some big implications. For one, it means we can calculate the exact likelihood of the generated data. This tells us how well the model captures the real characteristics of the dataset.
So we can measure how well the model is doing. That's super important for tasks where accuracy is key. And this connects back to neural ODEs, which are already a powerful tool in deep learning.
Yeah, the connection to neural ODEs opens up a whole new set of possibilities for using these techniques in different areas of AI. Now, all of these sampling techniques were put to the test when the researchers experimented with different architectures for their score-based models.
And they got some really impressive results, right? They mentioned things like FIR upsampling, rescaled skip connections, even borrowing ideas from the Big N model.
Oh yeah, the results were amazing. By tweaking these different architectures, they were able to get state-of-the-art performance on a benchmark image dataset called CFAR-10. They hit a high inception score of 9.89 and a low FID of 2.2050. Both of these are measures of how good and diverse the generated images are.
Wow, those are great numbers. And they even managed to generate high-resolution images at 1024 by 124 pixels, which is a first for score-based models.
It's a big deal.
Yeah.
It shows that these models aren't just theoretical toys. They can actually handle real-world data at scale. We've been focusing on the technical details so far, but you also sent over this other paper, Emerging Applications of Diffusion Models, which looks at the broader picture.
Right. This second paper is all about this so what. Why should we care about these score-based models and this ability to create something from nothing?
This paper is a perfect complement to the first one. The first was all about the how, and this one answers the why, and the applications they talk about. Mind-blowing, to say the least.
They really cover it all, from the obvious stuff like creating stunning visuals and making music to more unexpected things like designing proteins and solving complex optimization problems.
And it's all driven by these conditional diffusion models. These are basically score-based models that can be guided to create specific types of outputs.
So we're not just talking about random generation anymore. We're talking about targeted creation, like generating an image with a certain style or composing music with a specific mood, or even designing proteins with a particular function.
You got it. It's about taking these models and using them to tackle real-world problems. They even dive into how these models are being used in control and reinforcement learning, which is all about teaching machines how to make decisions.
So instead of just passively generating data, we can use these models to control things like robots, self-driving cars, or even entire systems.
That's the idea. And they highlight how these conditional diffusion models are impacting the life sciences. applications in drug design, molecule generation, even understanding protein structure.
They talk about protein design specifically, which is super cool. Imagine generating proteins with specific properties, like ones that can fight certain diseases or break down harmful stuff.
It's like we have this molecular toolbox for tackling some of humanity's biggest challenges.
That's an amazing thought. And one of the key ideas they emphasize is this concept of guidance in conditional diffusion models.
Guidance is all about giving the model a set of instructions, kind of like a map to follow as it navigates through that noise to create something new.
So we're not just letting it run wild, we're giving it some direction.
Exactly. The paper mentions a couple of types of guidance, like classifier guidance and classifier-free guidance.
What's the difference?
Well, classifier guidance uses, well, a classifier. It's a separate model that can recognize different features or categories in the data. It kind of acts like a supervisor, telling the model which way to go.
So it's like saying, okay, model, I want a picture of a cat, not a dog. And the classifier helps it stay on track.
Right. Classifier-free guidance, on the other hand, well, it does away with the need for that external classifier. It combines the learning of conditional and unconditional scores, which is a much more flexible approach.
Got it. And one of the coolest things they mention is that we can even adapt already trained diffusion models using guidance without having to retrain them from scratch.
Yeah, that's a huge time saver. It speaks to the flexibility of these models and opens up a lot of possibilities for adapting them to new tasks quickly. But maybe the most mind-blowing application they talk about is using diffusion models for optimization.
Okay, this is where it gets really interesting. Optimization, that's all about finding the best solution out of a ton of possibilities, right?
Yeah. Think about finding the most efficient route for a delivery truck, or designing a building that uses minimal energy, or even optimizing your investments for maximum returns. It's about making the best possible decisions in complex situations.
And they're saying we can turn this whole optimization problem into a sampling problem using these diffusion models.
Exactly. Instead of searching through all those possibilities, we train a diffusion model to actually generate solutions that are likely to be good based on our objective function.
So we're training the model to be a problem solver.
Pretty much. And this has the potential to really change how we tackle these complex optimization problems across all sorts of fields. They even go into the theoretical side of it with Theorem 2, which shows how the accuracy of this optimization process is tied to the quality of the data you use to train the model.
So it's still garbage in, garbage out, even with these amazing models.
Exactly. The data matters. It seems like these diffusion models could have an impact on, well, practically every aspect of our lives.
It really does feel like we're on the cusp of a whole new era in AI. One where we can teach machines not just to see and hear the world, but to create it and understand it on a whole other level.
Yeah, it's true. And what's crazy is this is all still so new.
Right, like we're just getting started.
There's so much more to explore, so many potential uses we haven't even thought of yet.
It's like we've been given these incredible tools and we're just now figuring out what we can actually build with them. And this deep dive, this is all about giving you, the listener, a taste of what those possibilities might be.
Exactly. We covered a lot. From the nitty-gritty of how these score-based models and diffusion processes work, to those mind-blowing applications in fields like art and music, drug discovery, even solving crazy optimization problems.
It's a lot to take in, but it's important to remember that this is like an ongoing journey. What we know now is just a tiny piece of what we'll know in the future.
That's what makes this so exciting. AI is always evolving. The pace of innovation is unbelievable. So I want to leave you with one final thought to, chew on. If you could model and generate any kind of data, what would you create? What problems would you try to solve?
It's a question that should really get your imagination going, and hopefully this deep dive has given you the knowledge and the inspiration to go out and explore those possibilities.
Thanks for joining us on this journey into the world of score-based generative modeling. Keep learning, keep exploring, and keep pushing the boundaries of what's possible.
Who knows, maybe you'll be the one to make the next big breakthrough in this exciting field. Thanks for listening.